Everyone, thanks for coming to my talk. And my name is Uehara from University of Tokyo. And I'm going to present robotics from control, collective dynamics as a behavior. Firstly, let me introduce briefly about swarms. Swarm is a group of agents with locally interacted simple agents, where typically we can observe the scalable, robust, and flexible collective behaviors. Because of this simpleness of the mechanism, it allows a bunch of applications from color patterns in living things and through clock simulations and to human class dynamics. So swarm is one of the most fundamental and interactive system showing emergence. So we focused on the controlling swarms in this paper. With a situation with one predator and agents of swarms. So predator interacts with swarms, and swarms react. But like in previous researches, the focus is on the strategies of the predator agents. So how can the predator control the swarms? But in our paper, we focus on the dynamics of the collective agents. So we utilize the collective dynamics into the control methods directly. And also, when it comes to the real world application, we have to think about some dynamics also. So I'm going to show you new control method that can handle the collective dynamics. And also we analyzed the suitable conditions of swarms for control. Okay, for this objective, we introduced a reservoir computing scheme into the swarm predator play systems. In this system, the predator interacts with swarms that will be input to the swarm layer, which we consider as a reservoir. And we connect linear layer to the swarms state, and then that will be output of this system. We only train the trainable linear combination layer, so we don't do anything about swarms in the training phase. By doing so, we can extract the rich and complex computational resources of swarms. Yeah, I hope you guys get a concept of the eco-state property from the yesterday's keynote talk. Like when it comes to using the reservoir computing for the systems, it's really important to the system to have the eco-state property, which is the swarm has to forget the initial state to work well, because it is supposed to work well no matter what the initial conditions are. And I will introduce the swarm models that we used. In the swarm models, each agent sends the 4 kinds of forces. But the first one is separation force, which is the force between the agents as a repulsive force. And the second one is running force, which is the force from predator to the swarm as a repulsive force also. And we also introduced the 2 other kinds of forces. One is a forming force, which is the force binds the all agents near the origins, so that no agents can escape. And also we introduced a damping force, like frictions. And we focus on the separation force and the running forces because those are, and the separation forces determines the interactions among the swarms, and also the running force determines the interaction between the predator and the swarm. So we add the gain terms onto these 2 kinds of forces, like the last equation, and we change these gains and observe what it's going to be. As I told you, the predator movement is going to be input of this system. So we injected 2 kinds of limit cycles dynamics as a vector field into the trajectory of predators. Okay. Firstly, we did the open loop analysis with this system. So predator will be the input. So we injected the limit cycle dynamics as a velocity of predator, and we observe the state of the swarm and analyze them. And also we for using as a reservoir, we analyze ESP of this reservoir. specifically PESP. This is indicating how the swarm can cancel the initial conditions difference. So the lower ESP means the better candidates for the swarms, for the reservoirs. Okay, this is what we introduced for observing the state of the swarms. Like if we observe the state of the swarms in a traditional way, like just exploiting the position and the velocity as it is, it doesn't work for the reservoir because it doesn't have any ESP. So we change like this. Each swarm agent has its ID in the simulation environment. So each time steps, the predator calculates the distances between each agent and itself. And according to these calculated distances, the new IDs are reordered and distributed to each agent. So closer agents get a lower IDs. So it changes, the IDs are changed every time step. By doing so, each agent has a ID. It depends in the way of its relative positions to the predator. So we call this relatively ordered states, ROS. We call it ROS. And by doing so, the initial states can be forgot by ignoring the implicit IDs of the simulation environment. Okay, when we're analyzing it, we also want to know what is the suitable conditions for the reservoirs. So we introduced the order parameter of the swarm, which is called the polarization VA. VA ranges from 0 to 1. If VA equals to 0, it means the state is disorder, where the agent's directions are distributed randomly. If the VA equals to 1, it means the order, where all the agent's directions are aligned perfectly. So we're analyzing the relationships between ESP and the swarm's property, the order parameter. This is a result of what we got. We changed the running gain and the separation gain. The gain terms we introduced into the forces. We changed this pair of gains and analyzed the order parameter and the PESP index. So as you can see, PESP index, the lower glass, became the lowest in the area of the phase transition-like structure of order parameter. This is really interesting. So we can say the swarms around the critical phase of this phase transition-like structure are good candidates for reservoir computing. Also, we have to know this. Clearer transition, for example, like a blue and the orange ones, produces lower PESP. So these are the better candidates. Okay, when we see the real dynamics of the states, the top one is the ROS that we introduced in this paper, and the middle one is non-reordered states, which means the traditional way of observing the states. In our ways, it cancels the initial states difference of 30 samples, but like in the traditional ways, it cannot cancel the difference. So which means the ROS can forget the initial states difference to hold ESP. Okay, we did also the closed loop control, which is like when we get an output of this system, we inject those output into the next time steps predator's velocities. So it automatically continues this loop. And successfully, we managed to implement this closed loop into these kind of limit cycles. The left one is a cycle limit cycle, and the right one is a van der Pol limit cycles. Here is the evaluation phase, so it's now really automatically moving in closed loop way. And now we compare the performance of our new method, ROS, and the non-reordered states. And as you can see, the ROS is really superior to the non-reordered states compared to the performance. In this performance, we compare the we see how much the predator can track the trajectory of our desired trajectories. And lastly, we also analyze the performance of this closed loop control and the order parameter. And as well as the open loop analysis, we found the best performance forms are located in the area of the phase transition-like structures. And also, like the open loop ones, queer lateral transitions produced better performance. So here we can say the phase transition-like structure seems crucial in autonomous swarming control's performance also. Okay, let me conclude this. Ours cancel the initial conditions difference compared to the conventional ones. And also closed loop control was achieved with this, our new ROS. Okay, but like we have to mention this, like a ROS made observation natural in terms of the predator can observe this swarm's agents with distance. But we idealize this situation, so we have to say this. The predator observed the every agent in the swarm. That is the idealized point in this research. But yes, so we achieved the closed loop controls. So, and the suitable conditions for the reservoir computings, we can say swarms around the critical phase of phase transition-like structure performed better. And here is the one question for the future researchers. In this closed loop control, predator contributes to the swarms by observing the state in the special way, but also swarm have to contribute the system to be controlled well. Swarms can tune the interactions inside of the swarm itself. So we call this like Uuroborotic swarm control, like the Ouroboros as the initial myth of this, the snake eating its tail itself. So we have to figure out this mechanism and interruption and applications deeply later. Thank you so much for listening.